Morning.
Morning.
How are we?
It's Friday.
It's Friday. I'm told. Are we ready to continue with the deliberations as we set the bar high yesterday? I hope we're going to end the Friday on a high note. Apologies, we had a bit of some technical glitches, so we are running late, but for us to proceed from here on, let me just check if we know where we left off yesterday. What was the last thing we did yesterday?
Some presentations.
Posters. Okay. I thought you were going to say a dinner. All right. Allow me to take this opportunity to invite Dr. Ms. Chitaur. She's the HOD for the Cybersecurity Department. She's standing in for authority. She will be offering the opening remarks. Chitaur, over to you.
Good morning, ladies and gentlemen. As it's just been said, my name is Message Down for Prof. Sodi and and so we were listening yesterday and here at the web, people talking about AI taking over. It is going to take over our lives, it's going to take over jobs, it's going to take over our communities, and so on and so on. Is this really the case? Is AI taking over, or is it just doing tasks faster than we can? What is really the case? But I believe for the youth, AI is indeed, it's not taking over. Because for the youth, they are more dynamic, they are ready to change, give them a skill, give them a vision, they're ready to go. It is maybe more a threat to people like me, the middle-aged people, or let's say the more mature people. Yes. We are scared of change, like things as they are. We don't want things to change. We are comfortable in our spaces. But I also believe that the ability for the human to think abstractedly is what trumps over anything else. So as long as AI is not able to imagine or reinvent anything, but to work within its parameters, there is no way that AI is going to take the human still be in charge. So no one is at risk. But even if it does take over, who says we cannot switch off the power? We cannot switch off the electricity. We have the ability to do that, reimagine our world, and we continue. So, ladies and gentlemen, good morning once again, and let me get back to the tasks I was asked to do, and welcome you this second day of the operations for the AI IndabaX for Namibia. So, Director of Ceremonies, Prof. Ndapa Nakashole, Dr. David Adelani, Dr. David Amfunda, Scott Richard Nakira, all protocol observed. Welcome to the second day and last day of IndabaX and Namibia. Wishing you good deliberations, sites, and Indabas. Thank you.
Wow, that was the student and precise welcome remarks. I was actually preparing for maybe just for my next introduction for the guests that you're going to be having, but all the same, if we just pick back what Dr. Shaw was highlighting in the welcome remarks, that we are not ready, or we are ready for AI, but whether we are ready or not, it's here to cover. Right. Allow me move with the program to have our keynote address from Prof. Ndapa Nakasole. She's an assistant professor, computer science, University of California in San Diego. Maybe San Diego, some of us have some issues. Not bad ones, good ones. I hope you're hearing us. The title of her keynote is The Origin and Impact of ChatGPT. I think it's the talk that I was waiting for is this one. So I don't want to preempt a speech, but I just give over the floor to Prof. Nakasole. Can you hear us? You can over.
I can hear you. Can you hear me? Can you hear me okay?
Yes, we can.
All right. Thank you so much for inviting me and for the introduction. So let me just share my screen here. I am delighted and very much look forward to talking to you about ChatGPT and also to hearing about your own thoughts and also the questions you have about it. I'll specifically talk about its history, the applications, as well as the potential impact on society. ChatGPT is an interface that allows us to talk to a language model. Right now, OpenAI, the company behind the development of ChatGPT, makes available two language models that you can talk to, GPT 3.5 and GPT-4. The ChatGPT application has already broken records in terms of adoption rate. It has seen 1 million users start using the application within the first 5 days, breaking the previous record held by Instagram that achieved the same thing within a period of 2.5 months. And these days, according to websites that track web traffic, ChatGPT is getting nearly 2 billion visits in a given month. So we said that the latest is GPT-4. So you must be thinking there has to be a GPT-1, and there is a GPT-1. There was a GPT-1. And this is the trajectory of ChatGPT. It all goes back to the transformer. That is step one. And what a transformer is it's a neural network. It's a type of neural network that is deep and it's specialized in processing sequential data. Sequential data like sentences. A sentence is a sequence of words. Sequential data like stock market data. When you have the price of a particular stock over a period of time, that is a sequence. And there have been other sequential data processing neural networks, but there's something special about the transformer, which is that it processes data that is inherently sequential, but in a parallel manner. It does so using something called the attention mechanism, whereby it can focus on multiple words simultaneously, yet still leads to a complete understanding of that sequence, of that sentence in the case of language. And with that parallel processing in the software, the transformer software, there's a perfect marriage that comes about when we have parallel processing in hardware like the GPU. And so given the GPU that processes, that is actually designed to do parallel processing, and the software like a transformer that can do parallel processing, we can have these models that can process data much faster than previous sequential data processing models, such as the recurrent neural network. And this is a merit that has resulted in the development of models like the GPT language model. One thing that's noteworthy here is that the transformer is a deep neural network. A neural network is a network that has this neuron, this simple processing units called neurons. Each one of these dots is a neuron. So it takes the input. This is a feed-forward neural network with the input being a sequence of words and output being a single word predicted by this network of neurons that are interconnected and working together to process and make some predictions and decisions. And by deep neural network, it simply means that it has not only two hidden layers, but many, many hidden layers. In a typical transformer, it's not unusual to have as many as 24 of these hidden layers. And the number of hidden layers, as well as the number of these units you have, determines how many parameters you have in a network. So in the transformer figure that you might have seen, you have this little n here, n times. It just means that these layers, these attention layers and feed-forward layers are multiplied and replicated n times to say that this is a deep network, a hierarchy of layers that process the input from this beginning here and increasingly extract the properties and semantics of the information that we put as input to create an understanding of that input. So given the software, the transformer neural network, that can process data in parallel, many language models have then been developed. One of them is GPT, which is short for Generative Pre-training Transformer. But there are others. The first one, the first pre-trained language model is Elmo out of the Allen Institute for Artificial Intelligence in Seattle, Washington. This bird from Google, Falcon, and Palm, which is a Google model. But there are many more language. But they are all crucially based on the transformer. So these are language models, but what is a language model? A language model is sometimes called a fluency device. It is a model that simply predicts if a given piece of text is plausible or not. Will a native English speaker say, yes, this particular piece of text is fine, it's an okay sentence, or no, this text should not exist, it's not proper English. So to understand what a language model is really doing, let's consider the following sentences. The first one is, Lola and Timo went to the store. This is a fine sentence. A native language speaker will say, yeah, that's an okay sentence. Second sentence, Lola and Timo go to the store. This sentence is using the irregular verb go and transforming it as though it were a regular verb. So this is a sentence that shouldn't exist. And a good language model should recognize it as such. It should say, no, this is not a good sentence. The store went to Lola and Timo. This sentence is fine in terms of grammar, but it's wrong in the sense that the store is a static object that usually doesn't move. And so this should not exist. 4, the ice cream truck went to Lola and Timo. An ice cream truck is a type of store, but it's a special type of store that is capable of driving itself to people. And so this is a fine sentence. And lastly, Etosha National Park is located in Arrangement. This sentence also, again, the grammar makes sense, but the semantics, in particular, you can drive to Arrangement and find that Etosha National Park is not located there. From these few sentences, what we are seeing is that a language model has to be really capable of doing a lot, has to know about grammar, has to know about categorical preferences and exceptions to those categorical preferences, as well as know about the facts of the world. Making decisions about what is plausible language turns out to be not so simple, and the language model has to be very powerful to be able to correctly say, yes, this is plausible language, no, this is not plausible. And to train a language model, what is done is the following. We are simply going to show the model a lot of these fill in the blank exercises. So we give it a sequence of words with a missing word. For example, we can show it the phrase, human infants drink blank, and we expect it to fill in the word milk. If on the other hand, the model predicts beer, we're gonna penalize it, we're gonna punish it, say that is wrong. You have to reconfigure your parameters, your connections in the network, so that next time you see this, you should predict the word milk. And this is the optimization step. The models are trained. This is the training step, are trained to learn to recognize what is plausible language by virtue of seeing billions and actually trillions these days of these fill in the blank exercises. This looks like a fairly primitive task, and you might wonder, why on earth would anyone want to perform this task? And the why of this task is very much evident, and we need to go no further than our own pockets. We in this room, very high probability, I can say that are using language models multiple times a day. Here I was typing in on my phone, the airport in Windhoek is blank, and here I'm getting suggestions such as located, and so on. These are perfectly fine predictions. And this is thanks to a language model, a good language model that's giving me plausible completions. Search engines also, with their query suggestion mechanism, are using a language model. So billions of people every single day using language models via search engines on their mobile phones, and in word processors. These are basically this basic task is already useful in this setting of sort of simply completing sentences. But as now seen, language models, when trained on a lot of data, are capable of doing much more than simply filling in the next word. So that is the what. What is the language model? And the why. Why would we want to do that? What about the how? How do we build a language model? So there have been several approaches that have been proposed to develop artificial intelligence technologies since the early days, the inception of the field in the early 50s. In those early days, rule-based systems were the thing. So someone sat down and specified the rules that will characterize the behavior of a system that will be considered intelligent. It turned out the rule-based systems were too brittle. There were exceptions to these rules, and there were exceptions to the exceptions. So they didn't generalize and failed in a lot of cases because real life is messy. Often things are not as we expect them to be. So what turned out to be a more successful approach is what is called machine learning, where the idea is that we're not going to be writing down rules. Instead, we're going to show data to the model. The model is going to discover patterns in the data, patterns that characterize the behavior, that make predictions, detect anomalies, and so on, that we are interested in. And going even further with machine learning, deep learning, the type of machine learning that is manifesting a transformer, we are building these increasingly large networks, turned out to be even more successful. So at the core of machine learning is data. The idea is that we're not writing down rules, but we're giving data to the model. And by giving data, the models are going to discover useful patterns. So we start with data and we give the data to the models. And these models, it's important that these models are highly capable of learning and making predictions. In this case, in language models, it turns out that the transformer is very capable of learning the functions that we're interested in. In this particular, we're interested in learning the function of, given a sequence of words, predict the next word. This is what is called an autoregressive language model, predicting the next word. But there are also other tasks where we might want to detect anomalies in data or discover trends. All of this can be done by simply feeding data to a model. And this is a very powerful paradigm, solving problems by simply feeding data to models. And data turned out to be a crucial and key ingredient for training these language models. GPT-3, for example, back in 2020, was already seeing 200 billion tokens. In other words, it was seeing 200 billion fill in the blank exercises. And these days in Chinchilla and other models, trillions of tokens are observed by these models in the training process. This is in contrast to humans. A 13-year-old is believed to have seen only 100 million words in their lives. So these models are particularly different from humans in this sense, that they need to see a lot of data before they can learn these general things about language. But as we know, they also have complementary skills and capabilities to humans. They can memorize way more than a human can, and they can read all these documents that a human might not have time in their lifetime, doesn't have the time in their lifetime, unless they spend all their time reading documents. So we said data is crucial. And the key advantage of language models is that the way the task is set up, we don't need any humans to label the data. We take the data as it is, news articles, scientific papers, medical records, social media. We simply want to see sentences. And for each sentence, we can create many of these fill in the blank exercises, as many exercises as we have words in the sentence. So we nearly have unlimited data, training data to train these models, to feed to these models, to learn about language. And so with this marriage, so we have this perfect marriage of, we have models that are capable of learning, which is the transformer, and learning from a lot of data, because the transformer processes data in parallel simultaneously. And we have the hardware that also processes things in parallel with the GPUs. And we have the data. We have lots of text data, thanks to the web that has grown quite significantly over the last couple of decades. And so we take the transformer, the model, take the GPU, we take a lot of text, and then we train a language model such as GPT. And that's the recipe. Well, how do we get from GPT to GPT-3? What the OpenAI researchers, but also other AI researchers in other labs, both in academia and industry, what was discovered was that if you make these models larger by perhaps adding more layers or adding more neurons, you can, if you increase the number of parameters of these models, then you're going to have models that are much more capable. GPT-3, with 175 billion parameters, was outperforming the earlier GPT models simply by making it larger and by giving it much more data. And some are saying this loss of scale in language models is sort of akin to the Moore's law as it applies to hardware and microprocessor speed. And what emerged from this scaling laws was that these language models trained more just to predict the next word. When they were big enough, at some point, they gained this capability where they could perform many, many tasks on which they were not trained. They were not trained on these tasks, for example, summarization or translation. But when the model is large enough, GPT-3, the GPT-3 paper, which won a best paper award at Neurospec in 2020, showed that there's this behavior, this sort of zero-shot learning behavior that emerges once you have large enough models. And this was truly fascinating, because at that point, to perform any task in machine learning, you needed data specialized for that particular task. But here is a model, very large, that could now perform any task, a single model for everything, as they called it. And sort of these scaling laws have also been observed in the only truly intelligent device that we know of, which is the human brain. And these scaling laws were kind of in the human brain were documented in a publication titled Evolution of the Human Brain When Bigger is Better. And the idea is that earlier humans had smaller brains. So for example, here we have a comparison of the brain, the size of the human brain, the modern human brain, and we have the brain of the chimpanzee. And what we're seeing here is that the smaller brains were inferior to the larger brains of the modern day humans. And the modern day human brain is truly remarkable. Starting from nothing, our species has done for itself remarkable things, going from darkness to light with the invention of electricity, going from walking long distances on foot, taking days, months, years to cover those distances on foot, going from that to covering the same distances in a matter of hours and days with airplanes and cars that are becoming increasingly highly capable of driving themselves with self-driving cars, going from being nearly wiped out by pandemics to inventing and creating vaccines and medications in a matter of months. This is truly remarkable. It's a truly remarkable device, the human brain. And this is why there's this obsession with the human brain in terms of artificial intelligence. It's all about the human brain. How can we replicate that? How can we get more of that good thing? Then we can perhaps improve the human situation even more. So scale has basically taken us from GPT-1 to GPT-3. We made it larger. And now we ended up with GPT-3, which can do many tasks. And these are tasks that the model was not trained for. It was not trained to do these tasks. Now, the model was trained in such a way that it was trained to predict the next word. It could do all these things, it's capable, but it couldn't really speak human language. It didn't understand humans in that way. So if I said, GPT-3, can you summarize an article for me? It will be just like, I don't understand you. I don't know. It might do something that you don't expect it to do. And so that is when this new field came about, which is the field of sort of subfield of NLP called prompt engineering, creating cues, natural language instructions that when crafted correctly, could get the language model do what we want it to do. Prompt engineering is truly sort of getting humans to speak the language of these models. And so because these GPT models, these autoregressive models are trained to predict the next word, it turned out that prefix prompts where we have some prefix words and a blank got us what we wanted from language models. So if I wanted to ask the language model, can birds fly? I would write something like birds can blank, and then it will fill out something. And so that's the idea of sort of prompt engineering. But OpenAI said, let's do the opposite. Let's not try to train humans to understand, to adapt themselves to the language of language models. Let's instead train these language models and to understand human instructions. And that is what got OpenAI to go from GPT-3 to Instruct GPT. Instruct GPT was trained by simply having OpenAI recruit a lot of humans. Those humans had to do the following task: come up with an instruction and the corresponding answer to that instruction. Instructions of the form: please answer the following question: what is the boiling point of nitrogen? And then the answer is in blue here. So by showing GPT-3 a lot of these instructions and their corresponding answers, it is adapted and instruction tuned to learn to understand what to do when given a particular human instruction and what humans expect when they give a specific instruction. Now, OpenAI could afford to kind of get humans to provide a lot of such examples to do instruction tuning, but this is truly expensive and also doesn't always work because there are tasks for which it's not clear how to specify those instructions and so on. So, and also there are some human some desirable properties that humans like. For example, humans like people to be polite, and so humans expect the model to be polite. Humans like people to be honest, so we want the models to be honest and not hallucinate. Humans want things to be safe. We don't want models to be proposing things that are harmful. For example, in general, society wants to be free of bias and prejudices. So these are things that we want from the model. So how do we get the model to reflect these human values? And that is when reinforcement learning with human feedback was introduced. And the idea here, this is a figure that you might have seen, is done in 3 steps. The first step is to do sort of what we talked about. This is instruction tuning. The model gives a human some instruction and the human produces, we give some instruction to a human and the human produces the desired output. And then we fine tune or instruct tune the model. In the second step, we are saying, how can we get more of that human feedback, but in a faster manner? We are going to get this instruction tuned model to produce multiple answers for a given instruction. And now all we have to do is give a human to rank or to grade these multiple answers for the same prompt. And so these human preferences are then used to train a reward model, a model that simply says, given some instruction and an answer from a model, give it some scale or score, give it some score to say 8, 0.2, and so on. And so given this reward model, OpenAI was then in a position to use reinforcement learning to tune the model in such a way that it reflects these human preferences that are encoded in the reward model because of these comparison data that was obtained from humans. And with that, there's now this GPT, what is called GPT 3.5, as a result of instruction tuning and modeling human preferences via reinforcement learning. And from GPT 3.5, OpenAI next got to ChatGPT, which is simply tuning the model on chat data. Why do that? People like to have a conversation. So if you think about something like a search engine like Google, every query is a once-off thing. There's no sustained conversation. It doesn't really remember what you asked previously. there is some remembering of history, but it's not in a conversational manner where you can go back and forth like you're talking to a person. And so ChatGPT is a model that is learned to chat. And additionally, it was learned it was trained to be safe, where OpenAI put in place some safety on top of GPT 3.5. So for example, if you are asking about something that the model feels like might lead to a harmful answer or some biased answer, it says, as a language model, I cannot answer that. So these are some of the safety mechanisms that OpenAI put in place in ChatGPT. There is also something called ChatGPT Plus, where the underlying model is GPT-4. GPT-4 sets itself apart from the previous models in that it's multimodal. As humans, we experience the world in a multimodal manner. We see with our eyes. We have ears, we hear things. And so here with GPT-4, it's a step in that direction, but it simply observes images and text rather than simply observing text. It is also believed to be much larger. GPT-4 is believed to have anywhere between 500 billion tokens to 1 trillion tokens. OpenAI hasn't disclosed anything about GPT-4, leading some people to now call it closed AI. So I want to say a couple of parting thoughts and a little bit of a discussion, but I would also like to hear your own thoughts. I'd also like to hear your own thoughts, so I'll keep this brief. A lot of people are concerned about potential impacts on their jobs. Will it take our jobs? Here, my take is that much like previous human innovations on this scale, there's bound to be some kind of transformation in the job market. Some jobs are going to be replaced, some jobs are going to be created. If we think about the digital computer, before then, there used to be lots of tellers in banks, but with the computer and the creation of the ATMs, we didn't need as many human tellers. Tellers lost their jobs, but programmers gained jobs to make sure that these ATMs were working correctly and no one lost their money. Also with education, as an educator, I have seen that students are now plagiarizing. Any written assignment, students are using ChatGPT, and because the models are good, the students are getting a passing grade by simply using these models. And that defeats the purpose, the learning outcomes that we want students to have at the end of the course. So there are some negatives, but there are also positives. These models are being used, for example, in the US, there's a nonprofit education organization called Khan Academy. They have partnered with OpenAI to use GPT-4 to create personalized tutors. And you can imagine that because this is a model, it is trained on a lot of data. It's more knowledgeable than any teacher you can imagine. And it's more patient and more empathetic. And so there are positives and negatives. On healthcare, also, there is a mental health crisis in a lot of countries. And there are companies that are using these generative models to create automated counselors. As with previous advancements in human history, we have to think about ethical considerations. How do we keep our society functioning in light of these advancements? How do we make sure that these models are not used for harm, but for good? How do we make sure that these technologies benefit everyone? How do we make sure that these models do not perpetuate inequity, but close those gaps? There are lots of exciting days ahead, but also lots of challenges. Thank you.
Thank you, Prof. Ndapa. Can you hear us?
I can hear you. Yeah, thanks.
Perfect. You have opened up a nice kind of a Pandora box for the deliberations today. There is a lot of mixed feelings around AI, and I like one of your kind of statement where you say life is a bit messy, and I like that. Really relating to what has been happening with ChatGPT, and we hear stories of some of the two lawyers that were disbarred because they cited two cases that never existed because they used ChatGPT. And as we can tell, the consequences of that, they're out of work. What would be your quick reflection on that? Of course, I was going to expect you to be one of the panelists. I don't know what the organizers did because I wanted you to dig more on these aspects. Maybe you could reflect on that for us. What's the implication? Of course, I think it touches also on the ethical aspects around ChatGPT use and AI in general, in a sense.
Right. Yeah, that's a very good question. Yeah, so so these models definitely hallucinate. They make things up. And so I think that's your question. About the panel, I would have been delighted to be on the panel, but unfortunately I have a flight in a couple hours, and so I had to go to the airport. But I'm sorry to miss the panel. So on your question, these models make things up, and those of us who work on language models and know that these models hallucinate, when developing systems and deploying them, I think there's a lot of precautions, especially if you think about healthcare. There are lots of models that are developed, but very few are deployed just because people see that there are lots of challenges still with especially with hallucinating things. If you're dealing with a high stakes domain where false information could lead to lost lives. So I think one of the things that have to be made clear, because these lawyers, I'm assuming, don't have a technical background, one of the things that we have to make sure of is to make sure that the public, because it's very attractive now to use these models because they are so good, and the language they produce is so fluent and just very much appropriate in a lot of cases, but it can do inappropriate things. And so that has to be part of the public education of using these models, that they make things up. I like one analogy that one person made about sort of how we can think of these models. So he said, with Google, with search engines, they kind of give us a link to an exact document and you can get that exact document. But these models, they have a parametric memory. They store this information in their parameters, but because the memory is limited, there are certain things that they have to predict. And when they predict, because not everything is stored, but rather sort of everything, the information is compressed. You have a lossy compression of the information into these parameters, and there are things that have to be predicted. The models then end up hallucinating and making things up. So this is one of the key challenges still that we have with deploying these models. When it's simply if you think about, for example, students plagiarizing, often the models are just almost right. So they usually the students don't get like a full credit, but they still get a passing grade, which is still frustrating, right? But the models are good, and but there's still that step that you have to take to fully deploy the system in real life settings and to make use of it in things like the case you're talking about, the lawyers using it in the courtroom. And this is some people call this sort of the last 5 mile or the last mile problem, which is that although the models are good, you still have to write a lot of glue codes to make sure that they are actually delivering for the domain for the applications that we want. And so that's one of the challenges right now, that you can do a lot of things, but to make sure that you do that one thing right, there's still you still need, you need expertise in the domain. You need very good programmers. You need AI experts and so on. So it's not that simple yet to kind of just say, I'm going to use this model in these high stakes domains and so on. So, but that's a good question.
Right. I have maybe one last question that I'll take from the audience. I have Prof. Mushala here. She's really nudging me to say she needs to ask this question.
Okay, awesome.
Thank you, Prof. I have two questions rather. One is more of a personal reflection from you in terms of what Khan Academy has done to train up a model to be a tutor for the students. What are the implications? What do you think about its capabilities? Does it have the potential to mimic the madness in the teaching? And will it not mislead the students who is monitoring his performance? Then the second one, who should be accountable for the hallucinating model? I'm not condoning the lawyers who are unethical in their practices, but at the same time, the model is owned by someone and they put it out there claiming that it has certain capabilities. And so people can trust it based on the reviews and the designers' recommendations. And then it hallucinates and they get wrong information. So should we charge the designer? Should we charge the owners of the community that subscribes to OpenAI? Takes accountability. Someone should go to court, right? And be charged.
So one question. Oh, it's done.
Yeah, awesome. Those are great questions. I think the first one is sort of in the education domain. Are these language models mature enough? Is the technology mature to deploy reliable tutors and help us in making sure that these are actually kind of models that can help students rather than kind of be a distraction to their learning. So I think that so actually education is one of the places where I feel like these models can can transform the whole industry. So as educators, because of the way, so basically I have to rethink my assignments because we can't ban students from using ChatGPT in assignments, but we have to rethink our assignments so that they require more of the human intelligence that we have that is sort of so creativity, for example. So if we think about something like ChatGPT, it's a model that basically says things that it has already seen. It cannot come up with new ideas. It cannot write a new paper that's going to be published at NeurIPS tomorrow because it only can tell you about things that have already been published. So it's not capable of being creative. So that means that it's really forcing us to rethink sort of what it means to deliver an education to our students. We have to rethink our assignments and so on. So in terms of simply being tutors, I think this is a perfect application for these models. They have read a lot of documents, and for standard information like this, often they are correct. They can, if you ask about basic laws of physics, or if you ask about computer science first year topics, it'll tell you these things with great accuracy. As I said, there's still you still have to do some cleaning up and so on. That's why this company, Khan Academy, has some codes to write. They can't just say, here's ChatGPT, use as a tutor. You still sort of have to wrap this in some clean interface. You have to make sure that it's not misleading and so on. But that work is very much doable, I think, in the education domain. And there's quite an opportunity for us to rethink how we teach, to rethink how we educate our students, and focus more on those things that are inherently human, in particular, true intelligence. Right now, as I said, the human brain is the only truly intelligent thing that we know of. And so we have to sort of change our way of teaching students to focus on those things that models cannot do. I think you had, the second question about who is responsible. So OpenAI is very clear about the fact that these models can hallucinate. They have a disclaimer. So so it's not, but some people are thinking, okay, so these models are not perfect. We have to stop developing them. That is not what we have to do, in my opinion. So these models are capable of doing a whole lot of good, but as with any advancement that has happened over human history, cars, there are accidents, they kill people. Airplanes, there's a crash here and there. And with fire, for example, it can burn down the whole house. It can kill people. And so here it's the same thing. And we can try to think about it in terms of how does it help us to make the human situation better? And so, for example, there's a lot of fear about models being biased and being perhaps perpetuating biases and being toxic and generating misinformation. So the other side of the coin, we can say these models can also be advocates of peace and human living in harmony and being we can think of it as like having a Nelson Mandela language model, for example, that advocates for peace or something like that. So so there's the good and the bad. How can humans are developing these models, we can make them do what we want them to do, can stop them from creating toxic content and make them models of peace or something like that. Maybe next time, the next thing that wins the Nobel Peace Prize could be a language model that's super peaceful. Or something.
I'm liking this discussion, and I'm afraid I might be carried away. I know there are many questions that are popping up from the audience right now, because you are really touching on quite interesting and impressive aspects, and really I would have loved to let this discussion proceed, because even Dr. Mgongo here is actually saying he needs to ask a question, but unfortunately we really are running out of time. We hope you were with us here in Windhoek, and we could also deliberate during break sessions, during lunch sessions, but all the same, we are very grateful that you managed to deliver this keynote address for opening our day 2 and really setting the tone for the discussions for the day. We actually want to thank you for your time. Thank you very much, Prof. Dapa. Yes, now moving on with our program, allow me to call upon Dr. David. Can you hear us?
Hi, yeah, I can hear you. Can you?
Oh, perfect. Right. You can share your screen while I'm just introducing your topic, and probably you could also maybe introduce yourself in the process. So, Dr. David Adelani is a deep mind academic fellow, University College London, UCL. So he's going to talk to us on natural language processing for under-resourced African languages. I think this really resonates with us in a very precise and direct way. We are looking forward to this speech, and I think it's also piggybacking on what the pace that has already been said by Dr. Alaswali. So, Dr. Adelan.
Okay, Thank you very much for inviting me. Um, I'm very glad that many people are interested in various aspects of natural language processing. And I think I will also continue with discussion about ChatGPT briefly before I delve into um, things about African languages. So why I wanted to just kind of motivate it with some of the things that is happening nowadays with large language models. We have seen great improvements in language models like ChatGPT, which has been trained on mostly English text and less of other languages. And then, of course, you can ask very complicated queries, like how to prevent COVID-19, and it gives you a lot of information, wear a mask, social distance, and so on, avoid large gatherings, which are actually correct. Then the question is, what if you ask the same question in another African language? So maybe you ask it in Yoruba or any other Namibian language. Interestingly, it also is able to give me some correct result, but not in Yoruba language. So it's saying wear a mask in public places, which is correct, but you can see that the answers are a little bit more brief than the one in English. Then let's assume I don't speak English language and I want it to translate it to Yoruba. Then actually it gives me garbage, actually things that are not actually correct at all. So for example, the second sentence has been translated to take white feather to their horse, which is completely meaningless and not related to the topic. So this shows that most of this technology are mostly working for English and other high-resource languages and not for many under-resourced African languages. But there's another question. What if this language technology is needed urgently? So going back to the COVID situation where when COVID happened, there's a need to suddenly translate basic health tips into many languages. And there was a lot of disinformation on WhatsApp and so on. How do you provide the correct information in a very quick way when we do not have correct or good machine translation models for many African languages? So this is a BBC article featuring one of our work. And this is the idea is to make our models to cover multiple domains. It's only when they cover multiple domains that we can be able to achieve quick adaptation to new domains of interest, including when we have a pandemic. So why do I work on research on other resource languages or other languages? This is very important for information access. Can you access information in your language? How do we integrate older people to access information on the internet? Can we also integrate it with the voice interaction system? Do we have machines that enhance human communication, like machine translation? And this is quite important. So I did my PhD in Germany, and the first few years, I don't speak any German, so you have to rely on automatic tools to translate your views and every other things you have to do. So it's also important for voice interaction systems, from text to speech to text. How would you be able to communicate with a mobile phone to achieve a task? Maybe you wanted to, you want an alarm in the morning, or you wanted to call someone or book an Uber for you in your own language. And this has a lot of potential in education, tourism, business, and in humanitarian responses. And another thing that's quite important, mostly to the linguists, is also understanding the linguistic structures of this language. And of course, this is very important, and also it's important to prevent our languages from dying. The linguists call it linguistic genocide. Why? Because if a language is not being used, again, it's like the language has died. And you will agree with me is that if your language is not covered by the recent technology, you would feel somehow that what's going on with my language? It's as if the language is about to die. And so that means we have a lot of work for us. We have to understand that this problem is really huge because we have over 7,000 languages in the world. over 400 are spoken by like 1 million speakers. But the interesting thing is that many of these languages, of the world languages, are either in Asia or Africa, and many of these languages can be categorized as endangered, and only 7% are institutional. So institutional because they are often used by government, schools, and mass media. But in terms of language technology, only less are supported by language technology. So how do we define under-resourced languages? So it can be simple as languages with less resources, but it can be in terms of data. How much on labor data do you have on the internet for this language for a particular task? Do you have like a sentiment classification data set for this language? And also, do you have enough web presence for this language that you can crawl monolingual text? Another thing is that in terms of research, how much research has been done on this language? Do we have like representation models that have been built for this language? Do we have task-specific models that have been built for this language and a particular task? And in some situations, there are no basic linguistic tools for some languages. Some languages do not have keyboards, spell checkers, morphological analyzers, and dictionaries. So this just tells you that a lot of things has not been done for this language. But the problem is bigger than that because, of course, most of these resources problem is data-driven. But the problem is, of course, bigger than that because there's also lack of representation of NLP researchers from Africa. If you consider the top ML and NLP venues in the recent years, you find out that even in 2021, we only have like maybe 12 authors with African affiliation. So that means less of this work on NLP is being carried out from Africa. Things are changing a little bit now, but I was told in the last that in the current ACL conference that there are still very few Black people represented, especially Africans represented in the conference. So, which signifies that we have like less than 1% of publications in NLP in 2021 that are coming from the African continent. So, under-resourced languages can be further described in terms of data. This is a definition by Joshi et al. In 2020, and they proposed like a six-class categorization of languages based on unlabeled corpus and labeled corpus. So the idea is that class 0, these are languages where you do not have any unlabeled text. Maybe this language you only have the Bible and nothing else in this language. And even the Bible in that language is not on the internet, so there's no web presence. So there are some languages that have very few texts on the internet. For example, maybe you have the online Bible that you can use for some tasks. And class 2 can be seen as a language with a few labeled examples and a few unlabeled examples. So, and this is how it has been categorized. So the class 0 can be categorized as left behind. I'm sure in Namibia, you will have some languages that can be categorized in that way, that because they have been less work done on those languages. And we also have like winners, which are class 5, like English, Spanish, Mandarin, French, German, and so on, mostly European languages. So under-resourced, so in terms of also research that has been done by Africans, if you analyze the NLP publication extracted by ACL Ontology, one thing you will find out is that in terms of the number of NLP publications per language, you find out that most research languages that people write on, initially, even people do not even state the language they are working on because they assume everyone is working on English. But now we have some rule like Bender rule that actually recommends that people will state the language they're working on. Most of the languages that people work on are just English, French, Mandarin, and a few European languages and a few Asian languages. There's no representation of an African language that is well researched. Because of that, we need to focus on NLP for our continent. So there are many reasons why we need to focus on this. Number one, we have over 2,000 languages, so we are just next to Asia. But apart from just having a lot of languages, there's a lot of linguistic diversity. We have many language families from Afro-Asiatic in the north, also Nino-Saharan in the north and eastern part of Africa. We have the Niger Congo from West Africa, extending even to southern part of Africa, where you have the biggest group called the Bantu family. We have the Khoisan. I think you might have some of this language, which are like with click sound in Namibia. And then you have like Indo-European, like Africans, and Austronesian, like Malagasy. But apart from this large linguistic diversity, one other thing we can see clearly is that this language is actually being used by many people. It's used by many people. If you consider the average language size by region, you find out that apart from European languages, our languages is the next set of languages that are being used. So that means if a language is being used by a lot of people, let's say over 1.5 billion people, but they are still underrepresented. So I think this is something that we should work on, especially as Africans. The reason why they are underrepresented are for many reasons. Number one, there's lack of data set for training and evaluation. We also have weak language policies by many African countries. For example, many African languages are not even national languages, not to talk of official languages in their countries. So we have lack of compute for developing NLP models and limited coverage in multilingual representation or language models like ChatGPT. Okay, so what do we do in NLP typically? From 2013 to today, it has been quite simple. We train a general purpose model, and then we can now apply this on different tasks. So this general purpose model is called a representation model, where you could, an example is the BERT model, where you could train a mass language model on a large amount of text using what is called self-supervised pre-training. And then you can fine-tune this representation model on a downstream task. Of course, you could add additional architecture like LSTM or a simple linear layer on top. And this can be used for sentiment classification, for question answering, and many, many other tasks. But what are the challenges of applying this framework to African languages? Again, one of the challenges is lack of data set to even fine-tune the model. Let's assume you have a representation model for this, no available label data to fine-tune the model. Secondly, there's no large enough unlabeled data that you can use for self-supervised pre-training. So you cannot even have a good model, a representation model for your language without a large amount of unlabeled data. So the only thing we can do is to leverage what is called transfer learning. That if a model has been trained on so many languages, then it should be easy to adapt to a new language that has been unseen. And this tends to work well. Lack of compute to even run them, because most African university labs do not have GPU compute to actually train these models. So in this talk, we want to address two major challenges. Number one, lack of data, of labeled data for downstream tasks. And here we make use of one approach called participatory approach, where we involve stakeholders, including native speakers, linguists, technology experts, in trying to build data set and models for our languages. The important thing with the participatory research is that even the native speakers who are the end users of the languages are involved in the process. And second challenge, there's no large enough unlabeled data for self-supervised pre-training. So here we develop a simple approach called multilingual adaptive fine-tuning to adapt an existing model to other African languages. So the first part, I'm going to talk about name native recognition data set for African languages, because this was done through what is called participatory research. So an NER is a core task in information extraction. It involves recognizing entities like personal name, location, organization, or date. It's a token classification task, as you can see on the right-hand side. you can recognize 4th of February as a date, Global Voices as an organization, Fernando Gomez as a person. And you also have the B and I prefix to determine if this is the beginning of the span or intermediate parts of the span. Evaluation is typically done using F1 score. So this is the situation of things in 2019 when I started my PhD. You find that we do not even have labeled data sets at all. So the ones that are available, like WikiNN, was automatically created. CMU Wilderness is for text to speech. It was also semi-automatically created from Bible data. And the others are either not free or they're just available on Linguistic Data Consortium where African researchers need to pay for them. So, but I can tell you that this is the situation here, and we even have more data sets. We have name data recognition, we have for part of speech, news topic classification, machine translation, sentiments, text to speech, and many ones that have been created mostly by the Masakani community. So what happened between 2019 and 2023? So we have some interesting initiatives on the continent that really help to power this. One is the Zindi ML competitions, where they try to organize competitions across different African universities. And this kind of encouraged people to release some of their data set for competition. We also have African NLP workshop that happens yearly. And one of the major artifacts at the end of the conference is that people release new data set that can be used for African languages. And Masakani is one of the primary drivers of some of these initiatives, especially the African NLP workshop. We also have some funding initiatives like AI for D, Lacuna Fund that are funding the creation of this data set. So Masakani is a grassroots NLP community for Africans, and by Africans, a pioneer participatory research for Africa NLP as an effective way to address this problem. The very first successful project was on machine translation, where they encouraged people, completely novice, to develop empty models for their language. And this was quite successful. And then we then extended it to creating data set for our languages, using entirely volunteers that contributed to creating data set for their languages. The first successful project is the name data recognition. So the data set covered, first, why do we need to create a new one? The previous annotated data set has some issues. WikiNN, for example, is automatically annotated. So we want something that's humanly annotated, and it's also very small. We have the Sadila data set, which is only for South African languages, and is based on government data. Then we have the Lorelli data set, which is not publicly available. So we created Masakara, the first NER data set for African languages. And the very first project was done by volunteers and native speakers, and we have very high inter-agreement score. Here we had like minimum of 2 annotators per sentence. So the Masakana project, like I said, we use the participatory approach. That means we have different stakeholders, native speakers, linguists, and language experts, NLP and machine learning experts, and researchers from all over the world, with representation from the United States, Canada, and many from Africa who are volunteers that contributed to the data set. We have also in Europe, I was in Germany then, and we also have a few contributions from Asia. And I was privileged to lead this collaboration between over 60 authors, and it was quite successful and influential in terms of the very first large-scale data set for African languages. So the Masakana project is in 2 phases. We had Masakana 1.0. So data set is a small data set. We had like just 920 to 3,200 sentences. And basically, it covers like mostly languages from West Africa and East Africa. But while doing evaluation, we found that our data sets actually do not transfer very well to Southern Bantu languages because they have some very interesting linguistic properties. And we are thinking of how do we address some of these regions that have been excluded. So we decided to expand our data set creation to 20 languages, and then which is larger. So we have over 4,000 sentences and also cover more regions of Africa, in West Africa, and also the Southern Bantu languages. So some of the language characteristics of some of the language characteristics that are important for NAR are the following. The way to think about this is you have an English model that has been trained on English text. How can you adapt this to different African languages? There are some challenges. Number one, you have a language that uses another script, like Amharic is based on non-Latin script. We have languages that are morphologically rich. I know some languages in Namibia are also morphologically rich, like Oshiwambo. And we also have like languages that, apart from being morphologically rich, they have noun classes. For example, you have this U before Zang and Ku before Zang in Xhosa and Zulu. So, and actually this affects the adaptation of any English NER model to this language because they have a different feature from the English language. For example, there's no prefix before nouns in English and actually affect adaptation. So we also have languages with a lot of diacritics. So there's some challenges for this. One of the challenge is actually when coordinating this project, we had to work with people that speak French. I'm not a native speaker of French, neither do I speak it anyways. So then we have to look for a bilingual speaker that can help us to coordinate projects. So language could be a barrier. So another issue was working with non-Latin script. So for me as a coordinator, it was very difficult to verify what has been done, if it was correct or not. So you need to like really train an expert in that from that region to be able to coordinate the project. So we also have one major issue with the participatory research is that participation is often for a short time. These are volunteers that are passionate about their language and you cannot tie them down. So maybe they only have time for 1 month, anything they can do in 1 month, that is it, and they're done. Then, of course, some have their regular jobs, so they can only contribute maybe a bit of their time for this work. And also, that's why the output is often small, a small annotated data. But even if the output is small, it's very impactful because our models are becoming more data efficient. That any data you have in that language is very important for adaptation. So another thing we did was to acknowledge annotators as authors of the paper, which is a top conference or journal paper, and this was highly motivating for our volunteers because this could also help them to advance in their career. So for the models, we make use of baseline models, which are very common, like CNN by LSTM CRF model. And we also fine-tune portrait language models like multilingual BERT and XLM Roberta. So typically, these portrait language models do not cover many African languages. So one way to improve over them, over the baseline, is to do what is called language adaptive fine-tuning. Basically, you can take an existing model like multilingual BERT, and then if the vocabulary is not supported, for example, Amharic script is not supported by multilingual BERT, you can swap the vocabulary or extend the vocabulary of multilingual BERT and then fine-tune the BERT on this new language. And you fine-tune on only the monolingual text in that language. After that, you can create something like an Amharic BERT, and then you can now fine-tune this on a downstream task. And this is quite very effective. So we proposed this initially in our LRAC paper in 2020, but also this has been adapted to different domains and different tasks, and this is very, very effective. And then we now have a time in NLP that don't stop retraining because you can easily adapt to a new language, to a new task, to a new domain by doing additional pre-training on a monolingual text. So some of the results is this. One thing you can see clearly is that pre-trained language model like multilingual BERT or XLM Roberta often give better performance than traditional deep learning models like CNN by LSTM CRF model. However, If the script is not supported, like multilingual BERT does not support Amharic, you have an F1 score of 0 because tokenization fails. And then suddenly CNN by LSTM CRF model gave better results. However, if the language is supported, they typically have slightly better performance than the protein language model that doesn't support this language. The situation of Yoruba is very similar. Yoruba is supported by multilingual BERT, but it's not supported by XLM Roberta, and that's why it gives slightly better performance. If we exclude the script issue, we find out that there's no big difference between either using multilingual BERT or XLM Roberta. So one way to improve over the script issue that led to F1 score of 0 for Amharic is to use this language adaptive fine-tuning. And we found out that this is quite effective when we first change the vocabulary of multilingual BERT to that of Amharic script. And we did adaptive fine-tuning. And this actually gave us a boost of 60%. This approach is also quite effective for languages not seen during pre-training, like Rwanda, including morphologically rich languages like the Bantu languages, and languages with small unlabeled corpus, like Wolof. For the Wolof case, we only had the Bible, basically, and it was still quite effective for adaptation. However, if this pre-trained language model has already seen the script, it's often better than any adaptation you can do. So if you can see, compare the result for Kinyarwanda and for Wolof, you find out that adaptive fine-tuning of multilingual BERT gave the best result. However, for Amharic, adaptive fine-tuning was not as good as XLMR base. The reason is XLMR base already supports the script. So and it's a big lesson for us that we should often include more scripts during pre-training when building language models, because doing adaptation at a later stage may not be very effective. Okay, so we also did zero-shot transfer on Masakhana, and the assumption is that we do not have any training data set. How can we benefit from existing data sets in other languages? So we compare the performance of using an English model, NER model that has been trained on English language, to using a language that is geographically or linguistically close to a target language. And we did evaluation on Masakhana 1.0. So for example, like Igbo, we found out that if you use Swahili or Hausa for adaptation, it often gives much better performance than using English. And the reason is, for example, for Hausa, it can be easily explained. Hausa and Igbo are in the same country, so they are geographically close, although they do not belong to the same language family. And they share a lot of entities, like the president's name, the governor's name, a lot of city names can be very helpful for adaptation. For Swahili, it's also in the same language family, Niger-Congo family, like Igbo. So showing that if you want to do adaptation, it's often better to use a language that is linguistically or geographically close. The same applies to Rwanda, where Swahili is better because they are from the same Greater Lake Bantu family. So just to wrap up, does Masakhana 1.0 transfer very well to Masakhana 2.0 because we created two versions of this data set? The way to think about this is we train on all Masakhana 1.0 languages, and we want to evaluate on Masakhana 2.0 languages. And of course, the baseline will be we train on all Masakhana 2.0 languages and evaluate on Masakhana 2.0 languages. And we want to check what will be the difference in performance. So first, let's talk about the languages in Masakhana 1.0 and Masakhana 2.0. So if a language is covered in Masakhana 1.0, then you would expect the adaptation to be very good for the languages that are in both data sets. So you find out that the adaptation is really good. Most of the time, you have more than 76% in adaptation. We only had a small drop for Hausa just because the newspaper we use for annotation is slightly different. However, if you consider languages not in the Masakhana 1.0, So these are languages that are just newly added in Mastercard 2.0, especially from the standard Bantu languages like Shishona and isiXhosa. You'll find out that the transfer is worse. And one of the reasons is because some of the features we have in the standard Bantu family, like especially the Nguni family, where you have this prefix before the named entity or the nouns. And if you're trying to adapt from a language that doesn't have this feature, it often leads to a worse transfer. Okay, so in summary, we have described how we created typologically and geographically diverse annual data sets using what is called participatory research. We also presented some baseline results and consequent transfer results, which shows the benefit of scaling our benchmark to typologically and geographically diverse languages. I have two parts for this talk, but I went slower so that yeah, I think it's better I don't know if I have more time or I should probably just stop now because it's 30 minutes. Hello, can someone say something?
So you have about 10 minutes if you want to wrap up.
Yeah, I think I can stop or just continue depending on what I mean. I don't know your timing. Yeah.
Yeah, we have about 10 minutes to spare. Depends on how you want to spend it. If you want to make us maybe open it up for interaction, we can do that.
Okay, so let me try to briefly go into the second section, and maybe I can leave 5 minutes for questions. So the second section is how can we do develop a multilingual language model through multilingual adaptive fine-tuning, because we do not have large amount of unlabeled data set for African languages. This is based on our Colin paper, which also got Best Paper Award. So first, let's talk about some of the challenges of adapting protein language models. The very first challenge, which is very obvious, is limited language coverage in protein language models. And the implication of this is that languages that are in the pre-training often have better performance than languages not seen during pre-training. This can be related to what is called cost of multilinguality. That if you want to scale to several languages, you also need to scale the capacity of the model. And even if you have enough budget to scale the capacity of the model, there's still a problem that many languages do not have a lot of data to learn a good representation. So we often have significant drop in performance. Another issue will be hardware restriction, because this model is getting bigger and bigger, and it's not even easy to evaluate them. Also, this is a lot of potential for research in building more efficient models. So I will just focus on limited language coverage. In the last section, I talk about that we can improve the performance of protein language model using what's called language adaptive fine-tuning, where you can fine-tune a protein language model on a monolingual corpus using the same pre-training objective. But there's some limitations to this approach. It's difficult to adapt for non-supported script, as we have said for Amharic. Let's create a copy for protein language model for every language. So if you want to do adaptation for 20 languages, that means you're going to create like 20 checkpoints, which is of course not parameter efficient. And also, once you have adapted the model for a language like Amharic, it limits the cross-lingual transfer abilities of the adapted model to other languages. So there are several ways to address this issue. One way is to build a new protein language model that cover more languages and several scripts, but this is resource intensive. Another approach would be to use a more parameter efficient approach like adapters. And this is quite nice approach, interesting approach also, because you don't need to fine-tune the entire transformer block. You only need to add a new parameter called adapters to every layer of the transformer network, and you will only fine-tune that new parameter. And this is more parameter efficient. What we have proposed is a simple extension of the left, which means instead of doing adaptation of a Puerto language model to one language, why not do it to several African languages at the same time? And this was motivated by what was done for MBAT 25, that was extended to MBAT 50. But what we are doing is slightly different. We are not like extending the capacity of the model from, let's say, 100 to 120 languages. We're actually specializing the model for African languages. So for you to specialize the model, you need to pay attention to some things. What is the right Puerto language model to choose? Based on our experience with script, we decided to choose XLMR that cover all the major African language script. We also cover a lot of languages that have more than 50 MB on the internet, especially on Common Crawl. And our fine-tuning corpus is based on our filtered web archive called MC4 and news corpus. And with this, we're able to cover more regions of Africa. So our results, our evaluation of LAFT, which is a strong baseline, what you can see is that if you use LAFT, of course, you get better result than the initial XLMR model, except for English, because the model is already good for English. If you try the MAFT approach, we have very impressive results, very competitive, but of course, you can also see some drop in performance, especially for Amharic and Yoruba. But one thing you have to understand is that this is a single model instead of having multiple models for every language. And this is quite effective for even an African language not seen in the math training, for example, for Wolof. So one way to address this, we find is that if you scale the capacity of the model, the difference between the LAFT and MAFT actually completely disappears. One thing we find that if instead of doing the adaptation using XML base, if you do the adaptation using XML large, you find out that you can create a model that's either competitive or better than the LAFT approach, which helps us to achieve our goal. We have a single model that works for many African languages, and we don't need to keep different checkpoints for different languages. Our model achieves the state of the art across different styles compared to very strong multilingual models like REMBET and MDBeta, which came out this year. And we had better results for sentiment classification, limit recognition, and news topic classification. And when our model was used for shared task called AfriSenti, we actually had a lot of downloads. So we also extended the model for sequence-to-sequence model, where you could do the same adaptation from XML to AfroXML. You can do it for T5 model from MT5 to Afro MT5. And we found out that actually this improves the performance of machine translation models significantly, as you can see on this plot. Oh, and that's a summary of the second part, where we tackle a major challenge of adapting protein language models to other resource language by using what is called multilingual adaptive fine-tuning. So we address two major challenges of building language technologies for the resource languages. One is lack of label data, and the other one is limited coverage of African languages in multilingual representation model. We introduced participatory research as an effective way to address the first challenge, and multilingual adaptive fine-tuning to specialized multilingual representation models. Thank you. So, questions?
Thank you so much, Doctor, for this interesting work that you are doing. And I know we have a lot of upcoming researchers in the room that are interested to hear more on how they can also progress in this domain as well. Right. I'm opening up maybe for some good questions before we go for our tea break. I'm looking forward to those that are participating in the competition to take this opportunity to get more insights on what they can also do, seeing the good work that is being presented here. Okay, I have a question at the back.
Anyone that has question, just come here and line up. It will be much easier.
Thank you for your presentation. I just wanted to ask in terms of perhaps conversational chatbots, which can be fine-tuned to sort of like African languages. You look at models, perhaps like LGBT, Godel, and others, and you realize that these are mostly trained on English data. So what could be the best way to sort of fine-tune with African languages like in is there any other models? Perhaps one can use things like models like AfriCAT for conversation, is that possible? Provided also that this they take sort of the different data set, or how like each model you need to have a specific set of how you understand is aligned, which you have, because they're sort of like different different architecture to so to say, but the way they take in the data, you have to sort of like align it to for you to be able to do the fine tuning of this. Are there any other models that can be fine tuned, especially for
if I understand the question correctly, you're thinking of like large language models like ChatGPT have only been trained for English text, and how can you adapt this to African languages? Like you can use the second approach I propose, which is just you continue pre-training on large amounts of unlabeled text for that language, and also you can do some additional tricks like changing the vocabulary or extending the vocabulary to cover more African language tokens. Actually, this is quite effective because recently I saw a model called Clinical Llama, and where they try to even adapt like a Llama model to clinical domain by also just doing this kind of adaptive pre-training or fine-tuning. Another thing is that you could also use a more parameter efficient approach, because in that paper they even use something like LoRa, which makes the adaptation very fast. Because these new models are very large and they're very difficult to fine-tune. And I think this kind of approach might be useful for that session. Yeah.
Yeah, thank you very much, David. I really love the work that you do, and congratulations again on your PhD. That's good. Be happy for you. My question is, in most of the discussions that I've been to, a lot of, especially with the big tech companies, they are saying the collaborative or participatory approach is not scalable. What can you say about it?
Yeah, that's a great question. I think it's not that it's scalable, because, for example, we scale the participatory research from 10 languages to 20 languages. So it's scalable, but it's also more work, especially if you're working with volunteers. There are some disadvantages of working with volunteers because they only work when they have time and they can drop out of the project. So if you have a lot of volunteers, for example, I think we started with like 12 languages. Like we had to push out to have like 10 languages that completed the task. So we have to acknowledge that if you're using volunteers, they are only doing it because they have passion for this. And we don't overburden them because we're not paying them most times. But if you're paying them, of course, you have more control on what they will do. And you have to structure your project in such a way that, although it's very risky, you still have some success at the end of the project. So for example, if you want to scale to like 50 languages and you are able to come up with just 20 languages at the end of the project, this is a success, for example, in my opinion. So there are risks to doing projects in this way. But for African languages where there was no representation for African languages, even if you're only able to achieve 10 out of 50, I think this is already a big success. Yeah.
Thank you so much, Dr. David. For the sake of the time, we will end this discussion, and I hope these deliberations can still continue online, etc. Now we are taking a break for about 15 minutes. So according to my time, this is 10:48. 10:48. So we should be back by. Huh? By 4. 15 minutes from now is 4. Okay, I hope to see you. I will actually be calling you back after 15 minutes. Right.